Hello and welcome to this quick clip which goes through dynamic equilibrium, Le Chatelier's principle, and constructing the Kc expression for specific reactions in dynamic equilibrium. As always, make sure that you've watched it after you've done your independent study and done some notes of your own, because it's designed to back that up after it's been done rather than take you through it from the beginning. So the first person to come up with the idea of dynamic equilibrium was Henri Louis Le Chatelier. And he stated that when a system is in dynamic equilibrium and is subjected to a change from outside that system, it will readjust itself so as to minimize the effect of that change and restore equilibrium. In other words, equilibrium shifts to oppose a change. And it's also important to remember that when you're explaining equilibrium changes in exam questions, you always try and talk about equilibrium shifts and what change it's opposing. So it's opposing an increase in temperature or opposing a change in pressure. An example of this might be the position of equilibrium will shift to the right if pressure is increased as the product side has fewer moles of gas. In other words, you need to be careful with the language that you use. So if we consider this equilibrium as an example, we can graphically explain what happens at equilibrium. So here's a question for you. Grab a scrap piece of paper and see if you can write down in Word what's happening as the reaction proceeds to equilibrium. Think about including things about concentration and what takes place when the equilibrium is achieved. Pause the clip and then resume when ready. So obviously we can start by saying that there's no nitrogen dioxide and there's only N2O4 at the beginning. So as the N2O4 is used up, its concentration decreases and that of the NO2 increases, as you can see from the shaded part of the graph. So the forward reaction slows down and the backward reaction speeds up until dynamic equilibrium is reached. So what's happening at dynamic equilibrium? First of all, the rate of forward reaction is equal to the rate of the backward reaction. The concentrations of the reactant and product are constant, but not equal to each other. It's also important to remember that temperature is also constant. So now moving on to the construction of the Kc expression, you'll remember that Kc is simply a ratio of the concentration of products over the concentration of reactants. So concentration is usually denoted by square brackets. So let's now write the Kc expression for this reaction. So we end up with a ratio that's expressed as a fraction, and just like in maths, because it's a mathematical expression, we have a numerator and a denominator. So in this case, the denominator has two concentration terms, and the numerator, the top part of the expression, has two concentration terms, and the bottom, the denominator, has one concentration term. Why is this? Because the expression in the top part of the expression, the NO2 concentration, is squared. It's multiplied by itself, so there's two of them. And the concentration term in the numerator is squared because there's 2 moles of NO2, which can be clearly seen from the equation. So if we take moles per decimeter to the -3 as the unit of concentration, and we put that in instead, we can obviously cancel out. So by getting rid of one of the concentration term units in the numerator at the top and the only concentration term unit in the denominator at the bottom, we're left with moles per decimeter to the -3 as our units for Kc. Okay, so that about takes us to the end of the first year review. Now we can start moving it on a bit to the second year. We're going to stick with this particular reaction. We're going to give this particular clip a theme. We're going to stick with this N2O4 going to 2NO2. So this is a typical exam style question. It gives you some data, it refers to an equation, it will give you the equation in the question, and asks you to calculate Kc under these conditions and find its units. It's usually around 4 or 5 marks is allocated. Now there's a specific series of steps you've got to take. We call it the ICE method. I'll talk about what the ICE acronym means in a minute. So the first thing we have to do is work out the moles at equilibrium. We're not talking about concentration just yet. You may have noticed that in the Kc expression they had concentration terms, not moles. That's an important point we'll come to in a minute. So let's first look at the ICE method. So using the data that you have, you can add in certain numbers in certain places here. So we can make this into a table. So in this case you probably already spotted that they've given you the equilibrium amounts present. It's quite an easy one, this. We'll do a more difficult one in a minute. So we've got the moles at equilibrium. It's been given, so we don't have to do the ICE method this time round. What we do have to do though is convert that into concentrations. So using the simple rearrangement of N equals V times C from the first year, we can do concentration as moles over volume. We're provided with the volume, which is 2 decimeters cubed, and we're provided with the moles of everything at equilibrium. So we can work out the concentrations at equilibrium. So the next thing to do is to write out the Kc expression like we did a few minutes ago. This time we need to insert the concentrations at equilibrium we've just calculated into that expression to get an actual numerical value for Kc. So I don't need to show you again how to get the units for this particular Kc expression because we also did that a few minutes ago. So now we can say that the value for Kc is 12.8 moles per decimeter to the minus 3. So now let's look at another example where you do have to use the ICE system. So we've now got another similar style of exam question. We're talking about a different reaction this time, but it's got some different data if we look carefully. So I've inserted what the question has given me. It's told me that I've got 0.2 moles of H2 and 0.4 moles of I2. And it also tells me how much hydrogen I've got at equilibrium. So I can put that data in the right place. At the beginning of the reaction I can also assume that I've got no hydrogen iodide to start off with. If you remember the graph we looked at a few minutes ago at the beginning of the clip, it had no product at the start. So to work out the change in equilibrium, all I have to do is take away 0.140 from 0.200 for hydrogen. That means 0.060 moles of hydrogen are used up. Now because hydrogen and iodine are equimolar, that must mean also 0.060 moles of iodine are used up, which you can insert there. Now at the same time, for every mole of either of them that are used up, 2 moles of hydrogen iodide are made. So you can double the 0.06 to work out how many moles of HI are actually produced, which you can now insert there. So now what you do, to go back to working out the number of moles at equilibrium for iodine and for hydrogen iodide. For the iodine, you take away 0.060 that's used up from your original 0.400, giving you 0.340, and obviously at equilibrium, because you've produced 0.120 moles of hydrogen iodide, that gives you that amount at equilibrium. In other words, you add them together, and that obviously gives you 0.120, like so. However, as I've said, this is just moles at equilibrium. We want concentrations at equilibrium. So dividing all of the moles at equilibrium by the volume of the total container, so the total volume of the mixture of gases in other words, which is 4 decimeters cubed, you get those values in moles per decimeter to the minus 3. So if we write out the Kc expression, I should say, you'll see that you've got the same number of concentration terms on the top and the bottom, so all the units actually cancel each other out. So that gives us 0.303 to 3 significant figures. Now it's really important that if you actually work out that there are no units, because the units on the denominator and the numerator cancel each other out, then you actually have to write in no units so the examiner can credit you for it. Don't just write 0.303, actually write in no units in brackets just to show them that you've worked it out. Okay, so hopefully this was reasonably useful to start you off. It's now a good idea to go and practice some examples so you can get the hang of this. Thanks for listening.